Hi, I'm Shahnawaz. In this lecture, we will study uh, what a functor is, and we'll do some examples of some important functors. So, if we have a category, suppose C, and a category D, and this functor is actually a map between two categories. So let us know this functor by F. So this functor is actually a map between two categories. So if we now what this functor does, suppose if we have an object say A here and an object suppose B here, it takes this object, so it takes an object A in C to an object FA in D. So similarly, if we have a morphism, suppose A and B are objects in C, and suppose there is a morphism G. Now it takes this morphism G, so this is the map F here. So it takes this morphism to another morphism between the objects FA and FB. So this it takes this morphism G to FG. So if we further, if we have another arrow like this, suppose we have an arrow from the object B to C, and there is this morphism say H. So this C is mapped to F of C by this functor. So this H is carried out to this F of H. Now we have this composition. First we compose G and then compose. First we apply G and then apply H, and here we can go from FA to FC by first applying F of G then F of H. So for this functor, we define it so that it should carry out this morphism to this morphism. I mean, this should be equal to F of H composed with G. So we want these two morphisms to be equal. So let us define this functor. So definition. So a functor say F between the categories say C and D is a map this F from the category C to category D, such that first item is F associates to each object A in the category C and object FA in the category D. F associates to each object A in C and object f of A in D. And similarly it takes morphisms to morphisms. Second item is f associates each morphism say f between the objects AB of C. This f takes each morphism between any two objects A and B of C to a morphism FA between the objects FA and FB. So it takes this morphism F to this morphism F of F between the objects FA and FB of C, such that so the first item is, suppose this is the object A and we have this morphism from object A to A, and this is the identity morphism. Now this object, let us do it in this way. So F carries this object A of C to F of A and D. So this is carried out by F. So on A we have this identity morphism IA, and on this object we have the identity morphism FA. So this functor must carry this morphism IA to I of F of A. So this I sub A is carried out to I sub F of A by this functor. So such that F, when operated on this identity morphism on object A, this should be equal to the identity morphism on F of A, and we want this composition to be equal. Second B, if we have so if we have a morphism between, so let between A to B we have this morphism F, and between B and C we have this morphism say G. That means this F is in home AB, and here this means this G is an element of BC. So if f takes this composition, say f composite with g to f of f composite with f of g, so this condition must hold. Now if condition b is satisfied this way, then this f is said to be covariant functor. In this case, this f is called covariant functor. So this preserves arrows in some sense. However, if this item b is satisfied in this way, I mean in the other way, that is if it is fg composite with ff, sorry, this is the composition g composite with f, because f composite with g is not defined here. So this is, sorry for this mistake here. So this is g, this is f, so this is g composite with f, because the composition g composition with f is well defined. So if this is other way around, like this, it is f of f f of g. So if item b is satisfied like this, then it is called contravariant functor. That is, it reverses arrows in some sense. In this case, this f is a contravariant functor. Now let us do some examples on functors. So examples. So let C be the category of topological spaces and D be the category of groups. So let us consider, so this is C is category, so this is the category C, so this is the category C here, this is the functor here, and this is the category D here. So if the category C is the category of topological spaces, so this is TOP, so we can take this category to the category of groups by taking the fundamental group functor. So this is fundamental group functor. Fundamental group functor. We can take also this category of topological spaces to groups by other functor that is called the homology functor. So this functor is this fundamental group functor is denoted by pi n. So we can use this functor as well, that is called the homology functor. So it is denoted by h sub n. Similarly, we can take this category to the category of groups using cohomology functor. That is h superscript n. So for example, if you take this circle S1, note that here this n appears, here also this n appears, and this n appears. So these are functors for each fixed n. So if we take n to be equal to 0, then it is one functor. If n is this little n is 1, then this is another functor. So we can take this topological space S1. So if I apply this functor, say h sub 0, so it is 0th homology group is just the group of integers. So using this functor, we enter from the category of topological space to the category of groups. So similarly, if I apply this functor, the first homology group, the other functor, we again enter in this category. Finally, if we apply this functor h2, then this category is 0. So similarly, for n bigger or equal to 3, we just enter in the category 0. So this category, this functor, in some sense, this creates a portal from entering. This creates, in some sense, a doorway to enter from one category to another category. So this fundamental group or these homology groups, this is what we are going to study in this course. So this is an important functor which we are going to study in the next lecture. So these functors, they just classify or characterize topological spaces using these algebraic objects. So one can associate these homological invariants to these topological spaces. So we can also take the category of groups, and we can enter in the category of, let us erase this. So we can enter from category C of groups to the category D of say K modules by using K linear representation functor. K linear representation functor representation functor. Similarly, we can enter from K modules to K modules by using dual space functor. Or from groups to free groups by using free group functor. Now there are other functors which are called forgetful functors. So forgetful functor. Now what this functor does, and suppose this takes the category of topological space to the underlying sets, so it just forgets about the underlying structure of the input category. So if we have the category of groups, so this functor takes this category to the category of sets, the underlying sets. So this is again the forgetful functor. Now there are two important functors which show up in algebraic geometry everywhere. So let us consider, so these are the two important functors. So let us consider the category C. And fix an object, say x in C. Now let us consider, now let D be another category. With objects, so this D has the objects of the form home, say x y, where y is it object of y is an object of C. So this D has these objects. Suppose it has object A, so this object A is gonna look like home of say x y1, where y1 is an object of C. So B is of home xy2. So this x is fixed. So this category D, it contains the set of arrows which come out from x. So now let us define a functor. Now let us define the functor C to this category D. Now this functor, we are going to represent this functor by home x. So here we can keep dash, so this is the spot where we are going to put our inputs. So this category C. Now what it does, it takes, suppose let us fix some object here, say y1. It takes this object y1 here to this object home xy1 here. So it takes this object here to the set of all arrows which are coming out of x. So this is carried out by this map here. So one can put it as, so one can denote this functor as this capital F. Similarly, so this is the case with object. So it takes an object y1 in C to an object in the category D. Now let us see Let us see the morphisms. Suppose we have a morphism, say mm, there are two objects y1 and y2. Let us write this in this way. Suppose we have two objects y1 and y2 in C, and this is the morphism G. So it takes this morphism G, which is from y1 to y2, to the morphism between, now this morphism is from y1 to y2, so we have to take this morphism from this object x y1 to x y2. So this is, sorry, this is home, this y1 is carried out to home xy1, and this y2 is carried out to home xy2. Now if we have a morphism here from y1 to y2, this morphism is carried out to a morphism, so let us denote this morphism by home xg. Now what it does, so if we have this morphism here, so this is from y1 to y2. Now we have here this is over x, now this is in y1, this is in so this is in y2. So we have so just like this. So this is y2 here, and this is the morphism, this is morphism G, this is morphism G. So it takes this functor here, this takes an element here from xy1, suppose this is the morphism f here, to an element xy2, so this is xy2. So this morphism is nothing but this is first apply f and then g. Now what this functor does, it takes this g to this gof. So this is this morphism, so this is actually this gof. Now what this morphism does, what this functor does, it takes this arrow to this arrow by via this map. So we are given g from y1 to y2, and with the help of this this functor here, we are able to carry out this functor f to gof. So this is in some sense this is a covariant functor. Indeed, this is a covariant functor because it preserves arrows, since we have an arrow from y1 to y2, and this is the morphism G, and this G is carried out to, so this G is carried out to home xy1 to home xy2. So this G is mapped to, so this is home x G. Now this is y1 to y2, this is again y1 to y2, so in some sense it preserves arrows. So this is a covariant functor. Now the next is the contravariant functor. So we will do the same process, but in the reverse direction. So here we considered D to be the category which contain objects like this, that is the for given object y1 it is carried out to the object home xy1, i.e. the set of all arrows which comes out of x. Now what we do, we define D to be the category such that this object y1 is carried out to the set of all arrows which are now landing in x. So here we uh, replace the positions. Here we take y1x, here y1 and here x, that is the set of all arrows which are landing in x. So this is a covariant functor. Now let us define another functor. Let C be any category and let x belongs to the object, x be an object in C which is fixed, let D be another category with, so object of D is defined to be the set, so it contains these objects home x y1, sorry, home y, this is x, where this y is in object C, is an object in C. Similarly here this D is defined to be the category consisting of the objects home x y, where y is in object C. So this is objects in D, object set of D. Now what this functor does, now let us define a functor. So we can define a functor, home C x. So this functor is defined from C to D. Obviously what this functor does, it takes let y1 belongs to object C. So when we apply this functor to y1, so this is home x, so this is gonna get mapped to home, so this is C here. So this takes this y1 to this set I to the set of all arrows which are landing in D. Obviously this is an object in C. Now let us see what is going to happen with these morphisms. Now let us let us suppose that we have a morphism, say G between two objects y1 and y2 of C. Now this y1, this is carried out to this object home y1x, and this is carried out to home y to x. Now here this is the functor home x, and this is the same functor home hyphen x. Now this map, this morphism G, it must be carried out to this morphism between these two objects here. So now we have to determine this morphism here between these two objects. So this is gonna get mapped to home gx. Now what this home gx is, so we have here we have this morphism between y1 and y2 g, and here we have y1 to y2, this is again g. Here we have y1 to x, say this morphism is f, and now then we have y2 to x, so this morphism is nothing but, so first we have, sorry, this is now we have to define this morphism here, so this should take a morphism from y1 to x, so this is f, to y2 to x, suppose this is g. So this should be, so this is, let us suppose this is, let us suppose this is the map f, and then this will be the map FOG. Now this functor, what it does, it takes g to this home gx, so home gx is defined to be equal FOG here, because when we have this map f here, which is from y1 to x, so we should get a map from y2 to x. So we should get a map from y2 to x. Now what it does, so it reverses the arrows. So sorry, it is not like that, it is here, this arrow is like this. Now we are done here, so this is home g of x, so it is like this, this is y2 x. Now it takes an arrow from y2 to x. Now from y2 to x we have this map f here, so it carries out this map to the map FOG here, which is same as home of gx here. So this in some sense reverses the direction. So here we have the map y1 to y2, so the directions here they gets changed. So this is y2 to x to home y1 to x, because it takes this map which is from y2 to x. Now from y2 to x we have the map f here, and it carries out this map, carries out this map to this map here. So FOG is a map from y1 to x. So this is a map from y1 to x. So this is the functor here, home, this dot times x. So this map is nothing but home gx. So here the arrow was from y1 to y2. Now here the arrow is from y2 to y1. So this does not preserve the direction of arrows. Hence this is a contravariant functor. This is a contravariant functor. These two functors, they show up frequently in algebraic geometry, and these functors are of very important use in algebraic topology as well as algebraic geometry.